Hello, everyone. What I want to do now is talk about the Baire category theorem and talk about the principle of uniform boundedness. Um, yeah, like Han Banach, the principle of uniform boundedness, is extremely useful in all different areas of analysis. In particular, we'll prove in probably the next video that using the principle of uniform boundedness, that weakly convergent sequences are norm bounded, which is something that is extremely useful in PDE theory. And I know, reading through Evans' PDE, it's a fact that is used constantly, particularly in nonlinear PDE theory. All right, so in case you haven't seen it before, I want to go through the Baire category theorem. Particularly because it has such a nice, easy proof. And yeah, so let's say M is a metric space. And I would say, I'm not the first to say this, probably more important than even the proof of the Baire category theorem is the kind of the philosophy of using the Baire category theorem. Kind of almost like dominated convergence theorem. It's as important as the theorem, just as important as the theorem is the philosophy of kind of using it and recasting things in terms of dominated convergence theorem, or particularly the dominated convergence theorem. This is kind of similar. So let's say M is a metric space. We have a little definition here that probably have seen, but if not, it's all right. So A is nowhere dense. If the interior of the closure of A is empty, a little more useful for us is that M take away A. So kind of we're saying A is really, really small in the sense that M take away A closure is dense in M. Right. So we have the following theorem. Baire category theorem. If M is complete, so it's a complete metric space, then you cannot write M as a union, the countable union of nowhere dense sets. Okay, and the proof I'm going to do is basically the book's proof. Okay, so the proof is as follows. A1, we're assuming, is nowhere dense. So this is, well, A1 closure is closed, obviously. So M take away A1 is open and dense. Right? Yeah, it's open just because this is closed. So nothing really there. So it's dense and open. So in particular, there is a point. It's not empty. Yeah, there is a point in it, and so there's a ball contained in it. So pick any, maybe to clarify, let's say it's non-empty. So yeah, so pick any ball. Let's give it a name, B1. Of radius less than or equal to 1. With B1 subset of M take away A1 closure. And again, M take away A1 closure is dense, so it's not empty, it's open. So certainly I can pick a ball of radius less than or equal to 1, where that ball, the open ball, is a subset of M take away A1 closure. Okay. Right, so we also have M take away A2 closure. This is dense and open. Because it's dense, it has a non-empty intersection with B1. And because it's open, and B1 is open, because it's an open ball, this whole thing here is also, maybe I'll use blue, this is also open. The intersection of, well, I mean, the intersection of any two balls is, any two open sets is open. And it's not empty, so. All right, so we're not being very judicious here. We just need to pick, we can pick any single ball whatsoever. B2, subset of this this intersection here, M take away A2 closure, intersect B1. With radius less than or equal to 1/2. And shrinking the radius of B2 if necessary. And replacing it, we can assume, well, B2 is a subset of B1, if it's a subset of the intersection, but the closure of B2 is going to be a subset of B1. Again, replacing this B2 that I'm circling right here with a smaller radius ball if necessary. Doing that, and I can assume B2 closure is a subset of B1. Right. All right, so yeah, just keep going. So just continue on. In general, you pick Bn is a subset of M take away An closure, intersect Bn minus 1. And again, this is open. This is also open. This is dense and open. So this is not empty. Right. Maybe just to clarify, right. So maybe to clarify, when I say a ball, I particularly mean, it's not empty. By that I mean you have a center. Right. So it has a legitimate center, so nothing is empty here. So we're taking the intersection again of two non-empty open sets. This one is dense here. So yeah, so the intersection is not empty, it's open. So we can pick a ball, Bn, shrinking it if necessary. We'll assume the radius is less than 1 over n, less than or equal to, and Bn closure is a subset of Bn minus 1. Right. Okay, so basically, I'll do what the book does. If you remember the nested closed sets theorem, equivalent to compactness. If you remember your if you remember the nested closed set theorem, you can basically just do that. Take the intersection of these nested closed balls. I'll do what the book does and basically, essentially, like prove that. So let's just summarize the properties that we're going to need. So like most of these proofs I do, I'm putting, it's a book's proof, but with more detail. So BK is a subset of BJ. K is bigger than J. Try to squeeze this in here. Bn is a subset of M. Take away An closure for any natural number n. And 3, I gotta move this up a bit. BK closure is a subset of BK minus n, which itself is a subset of BJ if K is bigger than J. Because K minus 1 then is bigger or equal to J. Right? So a particular BK closure, yeah, so maybe, right, like this, if K is bigger or equal to J plus 1. Being a little redundant here, really, I just need the closure of BK as a subset of BK minus 1. Okay, so the first claim is that Xn equals the center of my ball Bn. And here's where completeness comes in. And this is Cauchy, and this is pretty trivial. Why is this true? Well, let's look at K and J without loss of generality. K is bigger or equal to J. Sorry, K is bigger than J. So XK is the center of BK. Could very well be the only point in BK, but it is in BK. And BK is a subset of BJ. These are nested. Construction, these are nested. So this is subset of BJ. So what does that mean? That means, well, BJ consists of all points x whose distance from xj is less than or equal to, remember this has radius less than or equal to 1 over j. So we're saying xk is in bj, so a distance between xk and the center of bj, which is xj, is less than or equal to 1 over j. And that proves the claim. You know, this is Cauchy. All right, so let's say x is this limit. So let's finish up this proof by proving that x is not in a n. Right? And obviously, yeah, that'll finish the proof because that's all we want to do is prove that M is not in the union of the ANs. So how do we prove this? So let's assume X is an AJ, obviously a subset of the closure. Okay, well, by construction, BJ is a subset of M take away the closure of AJ. All right, so if X is an AJ closure, then X can't be in BJ, because if X was in BJ, then it would not be an AJ closure. All right. However, BK closure is a subset of BJ. For K bigger or equal to J plus 1, same thing, K bigger than J. That's just right here. So what does that mean? That means X is not in BK closure for K bigger or equal to J plus 1. If it was, then it would be in BJ, and we know that X is not in BJ. Okay, right, so last but not least, right, so let's use property 1. So B, or rather XK. So we want to get a contradiction. XK is in BK. That's a subset of B. Yeah, it's a subset of, so actually, before I do that, so in particular, X is not in BJ plus 1 closure. Okay. So if K is bigger than, or bigger or equal to J plus 1, so bear with me, sorry about that. Okay, so let's finish up this proof. Right, XK is obviously in BK. It's the center of BK, and BK is a subset of BJ plus 1 if K is bigger or equal to J plus 1. Right, and so this here obviously is a subset of BJ plus 1 closure. This is for all K. Well, actually, don't really need that. So this is true for all K bigger or equal to J plus 1. So that means x, which is the limit of xk, is henceforth might not be in bj plus 1, but it is in the closure of bj plus 1. And that's a contradiction to what's in the red. So that proves that x is not in, if I use k or n, but yeah, so I really like this little proof. All right, so let's put this to good use. I might give a homework proving that the rationals are not a G delta set using Baire category theorem. All right, so let's put this to good use. And some people have, like proofs of this principle of uniform boundedness without Baire category. I don't know why. I think Baire category is a really nice little cute result. Very elementary, yet incredibly powerful. So let's say X is a Banach space and Y a normed vector space. So we need X to be complete, so I can use Baire category theorem. Let's assume script F is a subset of B of X, Y. So some people call what I'm writing down the Banach-Steinhaus theorem. That's kind of, in the book, they use it for like a sequence version of this. I'll do that too. So, right, so this statement here, basically pointwise boundedness, meaning for each fixed x in big X, this supremum here now, I'm making no claim about taking the supremum over X in big X. But if this is true for each fixed little x in big X, then in fact the supremum of the operator norm from X to Y is finite. So it's uniformly bounded. So this is often stated as pointwise bounded implies uniform bounded. So this is a rather remarkable theorem. And in particular, you should note that B is kind of trivially, well, I shouldn't say trivially. You're going to interchange the supremums. You always can do that. Just 511. So this is going to be equal to supremum over all x equals 1 of this soup here. So what this is saying is, as long as this supremum that I'm circling, well, I mean, if it's bounded, so certainly if this supremum is bounded for norm x If it's bounded for each fixed x of norm 1, it's bounded for each x, because that's pretty trivial. It's not much to that. Assuming it's linear, that's extremely important. So for each fixed x of norm 1, if this is bounded, this yellow one, then just on the surface, there's no reason why the sup over all x with norm 1 should be finite. There's no reason why this is necessarily finite if this here is just finite, meaning that what I circled is a real number. Okay. What I circle in yellow, if that's a real number, then you're just looking at the sup over a subset of the reals. That might be infinity. There's no reason why it's guaranteed to be finite, but this principle of uniform boundedness theorem remarkably says that as long as this actually is finite for each x, then this supremum is bounded. This supremum is finite, rather. So it is a really remarkable theorem. Okay, so what's the proof? The proof is to, in a very clever way, use the Baire category theorem. So let's say AN is set of all little x and big X, where Tx is less than or equal to n for all t in script f. Right? So x and big X implies that this supremum is finite, so it's less than some n depending on x. Let's just abbreviate it as n instead of nx. But it definitely does possibly depend on x. That's our assumption here. So that implies that x is in a big N. So x is the union of the ANs. Great. We're assuming big X is a Banach space. So I can use Baire category theorem. So by the Baire category theorem, there exists an N where the interior of AN closure is not empty. And this is really the key to the proof. Right. So I'm going to prove in a second that AN is closed because I really want the interior of AN to be not empty. So pick epsilon 0 positive, x 0, and big X. So the other key to getting this to work is a clever use of linearity. So linear operators are rather special. Okay, so first let's prove AN is closed. Well, that's pretty trivial. So if I mean, I could probably even leave it for homework, but might as well do it. So let's say xk converges to x. Now let's assume xk is in AN, right? So t is continuous, and we have continuity of the norm. So because t is continuous, the norm of tx is given by the norm of txk. Well, xk is an an, so that means tx and norm is less than or equal to n. So that trivially proves, whoops, an. So that proves that an is closed. Take a limit point, x, prove that it's in an. So again, the point is, this is actually a subset of an. Well, it's a subset of an closure, which is equal to an. Okay, so let's finish this up. Yeah, so finally, if t is in script f, then I'm going to do this slightly different than the book does. They do it in 2 stages. I think that's a bit silly. Okay, so we want to get a uniform norm for tx, irrespective of x and irrespective of t in script f. Well, let's do something a bit trivial here. Let's use linearity in this nice trivial way. Multiply and divide by epsilon over 2. Why on earth would I ever want to do that? Well, we'll see in a second. So add and subtract x0. And use linearity. So it's minus. Use the triangle inequality. Oops. Well, the reason why I want to do that is well, if you know, you'll notice that if I subtract off x0, this here minus x0 has norm epsilon over 2. So by definition, this is going to be it has norm equal to epsilon over 2. Nothing special about 2. Anything smaller than 1 works. I just want it to be in this ball of center x0, epsilon 0. And it certainly is. Again, just subtract off, take this number here, minus x0, that has norm epsilon 0 over 2. So it's certainly in this ball. Well, x0 is trivially in this ball here. So thanks to linearity, we've kind of reduced the matter to just looking at x0. You know, it's almost like you're throwing away x and just looking at x0, which is kind of interesting. Well, this is a subset of an. So by that, in virtue of that, this is just going to be 2 over epsilon 0 n plus 2 over epsilon 0. Well, obviously that's 2n plus 1 over epsilon 0. This is independent of t, independent of x. As long as it has norm 1, we're fine. So absolutely trivially, this says that the norm of t, now understand, we absolutely need to assume that T is bounded to begin with. And maybe I'll do a counterexample to show you how we, to make that clear, that without assuming that F is a family of bounded operators, this fails. And this fails because here we need we absolutely need T as continuous here. Unless we assume T is continuous, there's no reason why you can do this. You just cannot, X is the limit of xk. You can't just interchange T in the limit. Okay? So the point here is you might think, oh, well, we don't need T to be continuous. We're proving it's continuous. We're proving, rather, it's bounded. We're proving each T is bounded in script F. No, we're not. We have to assume that they're bounded in order to get this uniform norm. But anyway, this implies that, maybe I'll write it like this. 2n plus 1 over epsilon 0 for any T in script F. That implies the soup here that implies that this here is bounded. In particular, it's less than 2n plus 1 over epsilon 0. All right, so I want to look at some applications of the principle of uniform boundedness. And it's a little strange, but what the book calls the Banach-Steinhaus theorem is usually considered what the principle of uniform boundedness is. And that is theorem, what the book calls the Banach-Steinhaus theorem is theorem 312. I'm not going to state it because really it's a very simple consequence of the principle of uniform boundedness. So after that, there is a really nice example example of using the principle of uniform boundedness on applying it to little c0. I'm going to do a similar example for big LP. And then I'll go over the classic example we did in the harmonic analysis videos on the existence of a continuous function whose Fourier series at really any point, let's say t equals 0, diverges, blows up to infinity. Okay, so in this example here, let's say P, and I'll give you something like this for homework, a little LP version of this. Right. So assume, and if you've never seen this, well, you're seeing it now. So a very important concept, local LP. So what on earth does it mean that F is an LP loc? It means that F is an LP over every compact subset of Rn. It's not necessarily LP over all of Rn, but over any compact or equivalently any bounded set, F is LP. So it's certainly measurable, and it's just LP on every bounded subset of Rn. Okay. So assume F has this really nice property that F times G is an L1, and still over Rn, but I don't feel like writing that, for any G in LP prime. Then F, in fact, is an LP. Okay, so if we have local LP and this then that means actually F is LP over all of Rn. Right? And the real main purpose of these examples is to get you used to translating these problems into problems involving the principle of uniform boundedness. Okay, so yeah, and if we're going to use the principle of uniform boundedness, we need a family of bounded, well, we need a family of bounded operators. So let's say Tn, probably the easiest thing to use here. I don't know if you can avoid using it, but is a family of bounded linear bounded linear functionals. So in particular, let's say Tng is going to be integrating over my x with norm less than or equal to n. G of x, f bar of x. Okay, so this is clearly a bounded linear functional. Just Holder's inequality. Well, I mean, yeah. So Holder's inequality says that this is actually pretty trivially less than or equal to the LP norm of this here, which we're assuming is finite. That's what it means to be in locally LP. Each one of these is finite. This is obviously integrating over a bounded set. Okay. Yeah, so this is a bounded linear functional, and we proved a few videos ago that in fact actually the norm from LP prime to C, the norm of Tn is actually going to be, let's call this Cn here, for lack of anything better to call it. This is just going to be Cn. Okay. Yeah, we did that. We did, forget if I said this was homework or maybe, whatever. I believe we did it though. I'm pretty sure we did it. Maybe we did the little LP version. Anyway, yeah, so, okay. Okay, so by dominant convergence theorem, this limit here well, this is just the following limit. Move this up a bit. Characteristic function, f of x, sorry, f bar, g of x. Well, we're assuming f times g for each g and L p prime is an L1. So by dominant convergence theorem, this is going to be just this integral here. So in particular, it's finite. It makes sense. There's no issues here. Again, by assumption, this whole thing here is an L1. Okay, so this implies that this here, the supremum, Tng, so that G is an L P prime, is, well, this, that. Yeah, sorry about that. This here is going to be, this family here is pointwise bounded. For each g, for each fixed g, this is going to be finite, and it's less than or equal to, well, fg L1. So the bound depends on g. That's fine, assuming this is finite. But that's kind of the point of principle of uniform boundedness. If we have pointwise boundedness, that's going to imply that we have uniform boundedness. So this is by the principle of uniform boundedness. Okay, well, this literally, as we said, this equals right. So we said this actually, this operator norm here, to remind you from LP prime. This is going to be equal to, this is going to be equal to the LP norm of this here. Okay. So what does this say? This says soup. Maybe put this in, put this n here. Make it a little more economical. Yeah, this is going to be finite. Sorry, LP, not LP prime. All right, so finally, by Fatou's lemma, so what do we get by Fatou's lemma? This here is less than or equal to the lim inf of this here characteristic function well, this is going to be, let's say this is M, for lack of anything better to call it. Let's do it black. Right, well, yeah, so this is certainly less than or equal to the soup, which is M. Well, M to the P. I'll stick 1 over P. Well, that's exactly what we need to do. We need to show that F is an LP, and we've done that. It says the LP norm of F is less than or equal to M. Right. So, yeah. So principle of uniform boundedness and understanding basically how bounded linear functionals work and their norms on LP prime, in particular, using the fact that this is true. Oops. gives us our solution. Tells us, yeah, that F is an LP. All right, so yeah, let me go quickly remind you of the divergence of Fourier series applications. And then I'll end off with a very important result, as I mentioned, that's very useful in nonlinear PDE theory, that weakly convergent sequences are bounded, particularly use that in Sobolev spaces. Apply that to PDE theory, particularly nonlinear PDE theory. Right. So just a little reminder, I'll go quick. So let's say F is in C 0 to 1. This is a Banach space. With the usual max norm, sup norm. And if you forget what that is, and I don't feel like writing this here, so I write infinity. Well, it really is a max because F is continuous, but anyway. This is a Banach space. Yeah, and of course I should maybe have mentioned, because right, LP prime is certainly a Banach space, so we can use principle of uniform boundedness. Okay, yeah, so remember what the Fourier coefficient is, 0 to 1, f of x e to minus 2 pi I n x. And remember Sn f of t. So this example is actually done also in the book on page 60, or maybe 60 or 61. It's page 60, 59 and 60. So they actually give a very quick review of Fourier series. Surprisingly quick. They do it in 2 pages. But anyway. Yeah, so remember Sn is partial sum of your Fourier series, so f hat of k, e to the 2 pi I k t. And remember, this was given by convolution with the Dirichlet kernel. Where, remember, not that important. Well, I guess, well, kind of is important. So I want to remind you it's sine n plus 1 over 2 s over sine s over 2. And when s is 0, we define it as 0 because, well, L'Hopital's rule says as s goes to 0, this is going to be 0. You should check that if you so desire. Well, actually, sorry, as s goes to 0, this is going to be, I think, I forget what it is, but I'm not going to do L'Hopital's rule in my head. Well, I think it would just be 1/2 n plus 1/2, or 2n plus 1, I think. Yeah, it's 2n plus 1 as s goes to 0. So anyway, this is going to be, well, anyway. Okay, yeah, so just like before, we're going to define Tn to be a convenient bounded linear functional. And nothing special about 0. It's just convenient. That's why everyone does this example with 0. As we did in the harmonic analysis video, you can actually define a whole family of these bounded linear functionals at different points, but yeah, just kind of keep this simple as an example of using the principle of uniform boundedness rather than really a deep fact about Fourier series. All right, so this is just simply 0 to 1 f of x dn minus x dx. Right. Okay, right, so pretty trivially, we have Tn f is, well, less than or equal to the, just the infinity norm on 0 to 1. So this is a bounded linear functional. So this is a bounded linear functional with norm less than or equal to d1. And I'll leave it for homework to prove, and nothing special about dn. But whenever you have a bounded linear functional that's defined in this way, I claim that it'll be a homework problem that well, yeah. So I should say this is actually continuous on 0 to 1. As I mentioned, redefining it at s equals 0, it has a removable singularity at 0. So we just implicitly define it as, again, it would be 2n plus 1 at 0. All right, so homework is, and I'll make this more precise in the homework, that in fact the norm, and this is not too hard to do, you basically have to approximate the absolute value function, or basically rather the sign function SGN by continuous functions. But we'll make that hint clear in the next homework. This here actually equals the L1 norm of dn. And this is also in the book. But remember in lecture that the L1 norm of dn you can estimate not terribly subtly. And it's going to go to infinity as n goes to infinity. And I believe it's bigger or equal to, I forget exactly. Book does Fourier series on 0 to 2 pi. I do it 0 to 1. But I believe this is going to be bigger or equal to, what is it? I think it was, certainly constant times natural log of big N for constant independent of N. Oops. Okay, so it certainly goes to 0, to infinity as n goes to infinity. Okay, so yeah, we're basically almost done with proving that there exists a continuous function whose Fourier series diverges at t equals 0. How on earth are we almost done? Well, what does this tell me? This tells me that, well, yeah, so if we have this soup here, like this, so this is bounded for any for all f and c of 0 to 1. Well, then by principle of uniform boundedness, we have that this here is bounded, and it's not. That's the point. Oops. Sorry, I did not mean that. I meant big N is in the natural numbers. If this is pointwise bounded for each fixed f, then it's norm bounded by principle of uniform boundedness. Well, the punchline is this is false. This is not bounded. It's bigger or equal to a constant times natural log n, so it's not bounded. It's unbounded. It goes to infinity as n goes to infinity. Okay, so this here, well, this is false. This can't, well, sorry. So I really like this proof because it's very clever that you're basically using principle of uniform boundedness in a completely opposite direction. You're not showing something is uniformly bounded by showing it's pointwise bounded. You're basically doing the contrapositive. You're showing something can't be pointwise bounded because it's not uniformly bounded. So this is false. This can't be true. So there exists f, continuous. I always forget if you can construct f or not, or you just know it exists. I think it might be much harder to actually explicitly write f down. You just know it exists. So this here, T and F, so in particular, yeah, I mean, Fourier series of f at 0 does not exist. Yeah, so we proved the existence of a continuous function whose Fourier series diverges at 0. All right, so I have one more application I want to do, and I actually is a bit I don't see this theorem really in too many textbooks. I think it's a good theorem. This is on page 61 in the book. Yeah, and we'll see why this is so useful in a second. Let's say X is a normed vector space. Don't even need it to be a Banach space, though in most applications is a Banach space, particularly PDE applications. Okay. So if we have the following, this is finite for all bounded linear functionals phi. So no claim of the supremum over all phi being bounded of this here. We're just saying for each fixed phi, this supremum is finite. This implies that yeah, it implies that A is pointwise bounded, norm bounded. Right? So this is particularly useful. Well, I'll just prove this and then I'll tell you why this is particularly powerful. And the proof is, yeah, it's very clever. Well, we can't use principle of uniform boundedness if we don't know that X is a Banach space. That's all right. We're not going to use it on X. We're going to use it on X star. X star is a Banach space. A perfectly nice Banach space. And I'm not going to look at this I'm not going to look at this set directly. I'm going to look at its embedding, the embedding of each little x in big A, the embedding of little x into the double dual. So remember, we call that X star star. So X star star is in the double dual, and obviously that, remember, is all bounded linear functionals from X star to C. And just to remind you, what is this? For any bounded linear functional, for anything on X star, this was just simply the only thing it really could be, just 5x. Right. Okay. So we'll get rid of that. Okay, so for all elements in my Banach space X star, this is a pointwise bounded family by assumption. Well, because remember, that's just the definition of X star star. By assumption, this here is finite for each fixed bounded linear functional phi. So again, by the principle of uniform boundedness, we get that this here this equality has nothing to do with the principle of uniform boundedness. This equality is what we proved, the isometric embedding of a normed vector space into its double dual. This is the soup. And to make clear, this is on big X. This is going to be X star to C. Well, this is pointwise bounded for each bounded linear functional. So principal uniform boundedness says that this, so do it like this, is less than infinity. So this is norm bounded. So yeah, a very important corollary. Definitely something to remember. And actually, if you go into Evan's PDE book, there's a really small review on functional analysis, and this is one of the results that he deems worthy of reviewing. I think it's literally like a 10-page review of functional analysis. Yeah, and this is one of the results he states without proof, just because it's so useful. So if we have a sequence, so let's say X, just like here, is a normed vector space. So if I have a sequence Xn and X, that converges to little x and big X weakly, then the supremum is finite. Okay. Okay, right. How do you prove this? Well, let's just say A is the sequence here. So by assumption, this limit exists. In particular, it's 5x. For each bounded linear functional. Okay, so in other words, what does this mean? This means that the supremum here is finite. For each fixed phi, because, you know, convergent sequences are finite. Or sorry, convergent sequences are bounded. Okay. So from what I just proved a moment ago, that means that this here is bounded. So weakly convergent sequences are norm bounded. All right, so that's enough of this. So I'll do another video on the closed graph theorem and open mapping theorem, and then we'll spend maybe a good 3 weeks on compact operators. Hopefully I will get to the spectral theorem for compact normal operators. We'll see. Yeah. All right, so long. Take care. Bye-bye.